Hey, how y'all doing today?
Doing good. How about you?
Doing really well. I got my last physical therapy session today, the last content in Stat 312 today, and it's some of my favorite stuff, but I seem to keep fricking saying that, so, you feel free to ignore me about what's my favorite. But there are a lot of really cool things in class today, and I'm not bummed, but there's like one topic that I think well, I hope to show you an example of it, even though we won't have it covered as anything formal for the class. I won't show you an equation. I might show you a picture. Okay. So I'm happy about stuff. And hopefully you are too, because again, the 5 week summer term is winding down rather quickly, in fact. So let's think. Administratively, I maybe I'll share a screen just to remind you of a couple things that you probably already are very aware of, but what the heck, let's do the reminder. And the reminder basically starts off saying, you know what, you got this test, okay, you should do it. And I tried to sort of emphasize with the different colors, hey, look, important stuff, big bold fonts. So yeah, exam will be live. It will be two 90-minute exams. I think you should get done in about 85 or less. You should easily be able to get done in that amount of time, because either you'll get to the point where like you've double checked everything and now you're starting to dribble check and you're saying, I don't want to waste my time, I'll just turn it in. Or you're saying, you know what, there's this one thing that I don't know, and I've already done my best to demonstrate I can answer a question related to this. So, that's a good place to be. So you'll know it or you won't. Okay. And most of you know most everything. So that's always good. So there are two parts. Exam 3, like we said, in the comprehensive final edition. basically it's a regular full-on final, twice as long as a midterm, but you guys in the summer Zoom slash online Canvas version will be doing it where you're going to say, well, I know this portion will be stuff we've looked at since exam 2. And so you might study differently and prep differently for the exam 3 stuff as the final. And you'll certainly have the opportunity to take a break between them. You could take a 24-hour break between them as long as you get them both done by 11:59 p.m. Saturday. Sample final exam questions that we can talk about in class tomorrow, and then the associated answers are there. And any questions about final coming up or anything like that? Okay. So I think Kirill mentioned yesterday problem 13 part B in chapter 9, and indeed in 13B ultimately he got the same answer that I got, and it's the answer that's built into my solutions. It's what the solutions are tonight. And so when you said that somehow the answer is different, the one thing I don't know, Carol, is where you found the answers being different, than the ones both you and I calculated.
I so I got the is this the answer that's the 20? The F statistic being the 20. I got the 20 by trying to do the jump software and doing
Oh yeah.
fit X and Y, but there's something wrong with the data set. I tried to stack them
Right.
and it doesn't work, so I gave up on that.
Okay, so if you did use the data set that's in the textbook, that is not really a data set. That's just a list of the means from each of the 5 treatment conditions and the standard deviations for each of the 5 treatment conditions. And so, yeah, it is likely going to result in doing something different. Our software, JMP, is really designed to work with if you had all 50 data points rather than just summaries of each of the 5 samples from the 5 separate treatment conditions. And so that could be the source of an issue. But yeah, I just checked that what the authors got is the same as what I got and you, and I think we're all good there. So if any of you were concerned, you don't need to be anymore. But if any of you want to follow up via email, that's absolutely fine. I wanted to also mention that if I click into the last bit of content, what we're going over today will correspond to some homework questions out of chapter 11. Yay! But those homework questions out of chapter 11 are not actually something you need to turn in. And so I'll have the answers online for you later today. So that way you can review your answers before tomorrow. So I'll put out the answers for you in the same way that I have answers to the earlier homework questions. And so you'll be able to check, but it's not going to be in a formal assignment per se. So tonight is the last homework assignment that's due, and it's material from chapters 9 and then a little bit into chapter 10. Anyone want to ask any questions about any of that? Questions from chapter 9 or 10 or anything administrative?
I was wondering if you can go over more about Turkey's method of like the understanding of it and how it applies to how we can use that to find a significant level of the comparison.
Well, I'll say it this way, and if you want to follow up, Anya, no, Anaya, Arissa, oh my gosh, name's bad. If you want to follow up afterwards, that's great. I think in the context of the lab, okay, you probably spotted something like the following. If you were coming up with the groups and you're listing them lowest to highest in terms of the average, the lowest mean was the hearing aid group, then the amputees, then no apparent handicap, then the wheelchair group, then the crutch group. And you maybe spotted that you had this sort of a pattern when you had sort of done that underlining thing at the end of Tukey's procedure. Okay, that was literally based on making a lot of separate comparisons. We compared H with A and saw no difference, H with N and saw no difference, H with W saw no difference, H and C and saw no difference. We compared A to N, A to W, A to C, N to W, N to C, and finally W to C. We made every possible comparison. And with 5 groups, that's 10 separate comparisons. Let's just think 5 groups. So sort of group 1 to 2, 1 to 3, 1 to 4, 1 to 5, 2 to 3, 2 to 4, 2 to 5, 3 to 4, 3 to 5, 5 to, yeah, 3, 4 to 5. Okay, I listed off 10 things and I went hog wild. Okay, 1 to 2, 1 to 3, 1 to 4, 1 to 5, 2 to 3, 2 to 4, 2 to 5, 3 to 4, 3 to 5, then finally 4 to 5. 10 separate comparisons. And the resulting, at the end of the day, analysis says here, you could say that there is a noticeable difference between the hearing aid group and the crutch group. Literally, the people with the hearing aids have a lower mean job qualification score than the crutch group. And that's the only difference we could spot. So across the 10 separate comparisons, it was only when you compare the hearing aid group with the crutch group that you see there is a difference between them. So for any of the 15 separate comparisons or contrasts, if you will, you could say mu1 versus say mu2, okay? We have a confidence interval for mu1 minus mu2, and that's going to be x bar for group 1 minus x bar for group 2, plus or minus a t alpha over 2 times degrees of freedom given then times the standard error for the difference. Okay, that's the procedure we're going to do 10 separate times. And you think, you know what? Across 10 separate confidence intervals, if we choose the confidence level of 95%, that's a 5% rate of error, that we will miss something 5% on each of those 10 procedures. Overall, the error rate gets pretty darn big. So maybe if we increase the level of confidence a bit, let's go to say 10, 99.5% confidence intervals. Okay, so yeah, literally we could choose the value of t to correspond to say 99.5%. The error rate would be 1/2 of 1%. And across 10 separate confidence intervals, we're going to have a maximum overall error rate of 5%. So the Tukey procedure basically says, we know we could be in error with any one of these confidence intervals. We know the rate of error. Let's boost our confidence level to lower the error rate for any one of the confidence intervals, thus lowering the error rate overall. And thus, we're 95% sure that all 10 confidence intervals, the result in our graph, will actually contain the mu I versus mu minus mu j that we're trying to capture. Okay, so Arissa, to summarize, the Tukey procedure, I sort of told a lie here. Instead of 99.5% confidence, it's actually another number because Tukey did a little bit of math behind it. The Bonferroni approach, if our textbook discusses that, it would say set the confidence level at 99.5. Tukey found a slightly better way mathematically. It's still in the upper 90s percentage-wise, but it says boost the confidence level, thus limiting the overall error rate across all of the procedures, all of the confidence intervals to only 95%. So I think that's the logic behind it, but I don't know that I answered your question in particular. So would you like to follow up?
Yeah, so yeah, the question for number 33 does elaborate that we should use the Turkey's method. So I assumed that we would use the equation that was shown in the book. It does involve Q, and I don't know exactly how we can get Q in order to get T.
Yeah. So let's just say Q, fine, it's a number in a table that you can look up, but let me just show you with a data set that you used on the lab activity yesterday, and that was discrimination and handicaps. Okay, so let's open it here. And the method of analysis you likely did was something like the following. Under analyze fit y by x, let's see if the scores are different across the handicaps. That would be the hypothesis testing way of phrasing it. Hey, are the scores different on average between the handicap groups? The confidence interval way of phrasing is, how are the scores different between the handicap groups? Just one would be answered with a yes or no. There's a difference, or no, there's not. The other says, okay, here are the estimated differences that we saw. I'm going to go ahead and turn on the mean ANOVA procedure. Okay. And like we said, you need to do under compare the means. Let's try every possible pair with the Tukey procedure. Again, the name is John Tukey, not Turkey. But you know what? I always find it fun when students say turkey because it reminds me of Thanksgiving, one of my favorite holidays, because it doesn't involve anything that takes a lot of effort other than cooking. But who loves cooking? Me. Okay, so our Tukey procedure, you can spot a lot of context here, but this Q star is basically saying, we're going to choose a value of T for you. What I call T alpha over 2 in my individual confidence interval, just use Q star instead. So plus or minus 2.80582 is my Q level. Let's actually go ahead and find out what confidence level that is for each of the individual confidence intervals with the probability distribution calculator. Okay. Okay, again, the T procedure. And I guess I need to know degrees of freedom here. And it's degrees of freedom for error. So here you have 65 for your T degrees of freedom. So I'm going to put in, okay, here we go, 65. And I want to put in a quantile and find a chance. And the quantile I want to put in here corresponds to 2.80. Well, let's just put it in 2.80. 582. Boom. So it says in the upper tail, we have 0.0033. If you take that error rate in the upper tail and double it to get a two-sided error rate, it's 0.006. Okay. Maybe I'll go with a central value to give you the confidence level. And I'll put it in a negative here. There we go. Boom. In they have to be, the lower one is the lower one. Okay, so individual confidence intervals, each of the 10 individual confidence intervals that you constructed yesterday were 99.34% confidence, and across the collection of them, the Tukey procedure says, and we have 95% confidence across the group as a whole. Okay, so if you're using raw data, the Q star value is going to be your Q value that you need. Does that sort of address your question?
Yes, it does. Thank you so much.
Yeah, no problem. I think the key is there's so many freaking things to know, and we can only know but so many things. I mean, have you ever met faculty members who are complete doofuses in certain areas, but they like know their own discipline? Not uncommon. And so when I wander in and talk to engineers and who are doing something that is beyond my ability, I just have to at one level say, okay, tell me what I need to know at the most basic level to move forward. And so you're getting a lot of content in this class. And if you guys remember about 80% of it, you are ABET approved from the point of view of the accreditation agency that says every few years, Cal Poly, you're good enough to offer degrees. Okay. Anyone want to follow up on any of the lab or homework related questions? Okay, so what I'd like to do is to move forward then in the content and finish us up for the day finish up for the term by finishing up for the day by talking about inference for regression. Okay, so if you're trying to figure out what a regression trend line is, we've already talked about our slope estimate. Beta 1 hat is just the correlation coefficient times the standard deviation of y over the standard deviation of your x values. And your beta 0 hat, your estimate of the intercept of the population trend line relationship is y bar minus beta 1 hat times the x bar value. We might have questions about usually beta 1. Okay, beta 1 in the context of our model says, well, yi is beta 0. The truth is beta 0 plus beta 1 times xi plus epsilon I. Maybe that's a really quick reminder of where we were at. Let's revisit this. If x is a person's height and y corresponds to their weight, beta 0 plus beta 1 times x is the average weight for someone of that height. There's a height-weight trend line. There's a height-weight trend relationship in the population of humans. And epsilon could correspond to how far above or below the trend line any individual is. So there's this population trend line with all of the pairs of values, x's and y's, in the entire population. But we only have a sample. And from our sample, we get the XY pairings and then come up with our correlation, standard deviations, means, and get our estimates of the intercept and then of the slope. No, let me rephrase that. We get our estimates of the slope and then the intercept in that order. A hypothesis testing question might very well be the following. Is beta 1 equal to 0 or not? That is a really common question, because what would it mean if the true underlying population trend line had a 0 slope? Oh, it means x is uncorrelated with y, that x is not related to y, that whatever the value for x is, the average value of y doesn't change. The average value of y would be just beta 0 if the slope is 0. On the other hand, maybe beta 1 is not equal to 0. That would be your alternative hypothesis. Okay. And then I guess we have to sort of pursue how we would test that hypothesis. And our test statistic is usually a comparison of what the data are saying to what the data would likely say if the null hypothesis were true, and divide through by some sort of a standardized measure of how far off our data estimate could likely be from the truth. That is going to be, as you would expect, a test statistic, T. It's a difference between our sample slope and the slope according to the null hypothesis, 0. Some of you are noting, well, you might not want to compare the slope to 0. Maybe there's a more generic delta 0 that we want to compare it to. But I'm sort of going to pitch things today in this simpler context. Let's suppose there is 0 according to the null hypothesis, no slope. There is either a relationship, alternative, or there is no relationship, null. My test statistic is a comparison of the slope we saw in our data set. We're going to compare that to what I would have expected if the null had been true. We're going to divide through by what we'll term the standard error for beta 1 hat. And we need to know what that standard error is. So I'm going to sort of show you, A, JMP will do all this for you. But B, let's talk about the standard error and its separate components. One part of the lab, the last part of the lab, asks you to sort of tackle this question. How do these following terms in the equation actually make conceptual sense? But let's just tell you the standard error is equal to S, okay, over then the root of, S sub x and the root of n minus 1. Okay, I think it's an n minus 1. I'm pretty sure, and it's in the lab. So if I got it wrong now, that's fine. You can fix it later in the lab. Okay. And conceptually, we don't know what S is. S here is the square root of MSE, and it's equal to the typical vertical distance between DIST, between y, the actual y, and y hat. So how far off are you if you're using your regression line to predict the y from your x? How far off are you by a mean square error or so? Okay. And darn it, now I'm thinking, I'm sort of obsessing. I apologize. I'm obsessing whether it's S or N or N minus 1 in that denominator. And I'm really, okay, I may come back and correct this in a little bit. So what we have in the upstairs is more variability in the trend line causes a larger standard of error or less precision. Okay, that makes some sense. The lab will walk you through a comparison, okay, that sort of gets after that. What else do we see in our equation here? N, if N is larger, if the sample size is larger, I guess we more precisely know the truth. And so the larger N, the smaller the standard error is going to be, the more precision we have. Again, that makes conceptual sense. What about that third term out there? S sub x, the standard deviation of the x values. Well, I'm going to sort of draw a quick graph for you that will try and convince you of that, but we'll see if you're easily convinced. If you were to go to the optometrist and sort of eventually be fitted for glasses, they'll ask you some questions before the fitting, and they'll say things like, hey, is this clearer and easier to see, or is that? And they'll flip like something on the sort of lenses right in front of you. And you say, no, A is better than B. And they get it down to the place where you can't really hardly tell the difference between the two of them. Earlier in that process, you can usually say, oh, that's better than that. If I have 10 data points to look for an XY relationship, and here's the true population relationship, and there's the true population trend line, would you rather have 10 data points all right in the middle, or would you rather have, say, 3, 4, 5 down low and 3, 4, 5 up high? If you have all of your data in a very narrow range, it might be hard to spot the real trend very easily. Your sample trend might be off by quite a bit with just a little bit of bad luck. But if all your data values were very low or very high, it's going to be hard to be too far off of the true underlying trend line. The more spread apart the x's are, the more precision you have in finding the XY relationship. Okay, so our equation here, the test statistic t, is going to be just the sample slope minus 0 over the standard error of the sample slope, standard error of beta 1/2. And let's show you how I could get exactly that. Okay. So let's go ahead and test the hypothesis. Actually, maybe not the building heights and stories. Let's use that one for the next example. Let's look at these data on the rainfall level and the corn yield in one particular county in Illinois over many years in history. And I'm not really focused on the rainfall as my predictor variable, but rather the year. Do we see higher yields in later years? Although probably none of you have taken the history of crop science class in whatever that department is, you can imagine that yields might grow over time because of, tractors or better plows or a harvester or fertilizer or irrigation. From 1890 to 1927, maybe the yields have been increasing. Let's go ahead and try that analysis. Our null hypothesis that we're going to be using that underlies this test statistic t, the null hypothesis is that there is no trend over time. The alternative hypothesis that I'm going to use is that there is a trend over time. I'm not specifying positive or negative trend. This is just JMP's default null and alternative hypotheses for a regression trend line. Your test statistic t is going to be quick to calculate. Let's get it done. under analyze, fit y by x, you're asking the question, does the year help me predict the yields? Is there a relationship between the yield and then the year? I click OK. I see what looks like a very flat trend. I mean, if I exclude those 3 data points down here, I'd say no trend at all. But maybe overall, we do see a trend. Let's fit that line. And you can see the line that's fit does have a positive slope. Some numbers of note to mention are root mean square error. That is the value for S that we mentioned in our earlier equation for the standard error. Okay. And the number of data points that you have, again, worth noting. Okay. R squared, our old friend, 14% of the variability is explained. Down here at the very bottom, though, we see an estimate. That is our slope. Our slope estimate, 0.1491. That's the beta 1 hat. And the standard error for beta 1 hat, what's in our denominator, is right next door. And literally, if you take the 0.1491 and divide it by 0.0605, that's going to be 2-point-ish. Okay, 2.46 is that actual ratio with a little bit more precision than I was telling you the numbers at. And the associated p-value with 36 degrees of freedom is 0.0187. And you know by now, with the p-value below 0.05, reject the null, believe the alternative. I would say at the end of the day, we have evidence in our scatter plot here strong enough to allow us to say we believe the alternative hypothesis. This slope that we see is steep enough that we're convinced the underlying population trend line across not just these 38 years, but years in general is a positive trend. Hypothesis test. I'm good with that. Any questions about the hypothesis test? Okay. So I want to move forward and talk about a confidence interval for a population slope. And sometimes your natural question could be written as like, hey, tell me what the slope is. But not just the slope in the sample, but the slope in the population overall. Okay. And I'm going to say a 90, well, better yet, 100 times 1 minus alpha % confidence interval for the underlying and unknown slope is going to be your sample slope beta 1 hat plus or minus we always have 2 parts in a confidence interval, the estimate plus or minus the margin of error, and the margin of error itself has 2 parts. One of them has to do with how certain you want to be right, and that's going to be t with alpha over 2 as the upper tail area and degrees of freedom that matches our DF error, or if you will, DF, here is DF error. In this case, with 1 explanatory variable, that's just going to be n minus 2, okay, degrees of freedom. And we're going to multiply that by the standard error for beta 1 hat, which you can calculate by hand, and I showed you earlier how to do it, or most likely you're just going to use the software, okay? So I could choose a confidence level, okay? And I'm going to say, here's my estimate, plus or minus about 2 standard errors. If we want 95% confidence, the t-value's about 2. So yeah, I guess as long as I have my values here, the standard error, okay, oops, wrong color. As long as I have my values here, the standard error and beta 1 hat, I can look up with my t distribution calculator. I can look up the value for t that I need to use, and I'm going to get a confidence interval. So let's look at in another example how I would come up with my beta 1 hat and my standard error. Okay, and then let's figure out the appropriate t value to use. Then I'll show you a way you could just get JMP to do the whole thing for you. Although the lab doesn't emphasize it and I don't encourage it, it's still not too bad. And we're going to go with a data set that we looked at earlier in class. We've got data on the height of a collection of buildings that are called skyscrapers. and the number of floors that the skyscraper has. So like 54 stories means there are 54 floors, and the height is 770. In this case, it's feet. Okay. Let me show you the procedure. Under Analyze Fit Y by X, we have our friend. Let's do it. The height I'm going to predict based on the number of floors. So that's going to tell me how tall a building is likely to be if I tell you the number of floors. Like ultimately, I can tell you, 45 floors, and you can tell me, oh, I'm going to predict, here's the height. I click OK. Boom. You see the trend line, and no, we don't see it. We see that a trend line would be valuable, and I'm going to add the trend line by adding the fit line, and that's going to sort of cause that trend line to be drawn in. We can see it sort of goes from quite low to high. Note here that the X value of 0 isn't displayed unless we force it to be displayed. And similarly, the Y value here, it doesn't start at the origin, so I'm going to have to sort of have the X0, Y0, if you will, the origin down here for us to actually see that the slope here is positive and about 100 or so in value. You would know that if you just looked at the parameter estimate for the intercept. It's 90 feet, 90.31 feet, plus 11.292375 feet per floor. The units is feet per floor. Okay, so I've got some of the numbers I'm going to need. So let's just go ahead and copy them over here. In our example here, switching to blue, I've got 292 plus or minus value for t. Oh, I started that way too high. 11.292 plus or minus. I'm going to leave the t value off to the side, but I'm going to multiply that by the standard error, which I see over here is 0.4844. 0.4844. In case you're worried about sort of rounding, okay, notice here the level of digits past the decimal mark that I keep. I'm keeping one additional digit over here. That will mean that after I calculate the product following the plus or minus, I could then round to the 3-digit past the decimal mark location, and I would have committed no rounding errors. Okay, so what is the value I'm going to use for the t? Well, it has to do with the confidence level that I want, okay? And it also has to do with the degrees of freedom I have, so I need to know degrees of freedom. If you have knowledge of 60 data points, you know that's 58 degrees of freedom, or you could just look in the analysis variance section and say, oh, degrees of freedom error, 58, good. 58 degrees of freedom. So let's see if I could find, darn it. There we go. My GMP probability distribution calculator here. I'm going to go with a T with, oh my gosh, I'm running out of space, 58 degrees of freedom. Boom. And I want to input a probability and get my T values out. And I'm going to have a central probability of 0.95, which tells me the T value I ought to use for 58 degrees of freedom is 2.0017. Okay, so let's remove that. And this, boom, 2.0017. Okay, so you could do that. You're happy to have done that. I just want to show you JMP inside the output, and I'm going to maybe make this smaller so it doesn't sort of overfill the whole screen. I'm going to go down to the very bottom. And I'm going to note here, this is a tool that I didn't know until just like 2 years ago, and I haven't figured out until earlier today. If I were to click on my graph here, okay, notice here under columns, I could turn on my lower and upper 95% confidence. So if you want to know 95% confidence interval for each of these two parameters, again, right click and under columns, turn on the upper 95%. I'm going to say my 11.292 plus or minus 2 times my standard error will give me a range of, well, just mathing it in my head, that's about plus or minus 1. So that's going to be about 10.29 to 12.29. The actual numbers exactly are 10.32 to 12.26, or if I want 3-digit precision, it's 10.323 up to 12.262. A lot of words. Let me put that in plain English. 95% sure that we have 10.3 to 12.3 feet per floor. Okay, 95% sure that we have 10.3 to 12.3 feet per floor. And no, oops. Well, that's meant to be a slash. There we go. Feet per floor. So knowing that we have units in the slope, and the units is always y per x, or feet of height per x, floor per floor, that's going to give you the ability to interpret this. And again, construction management majors say, yeah, that makes sense, because in some of those older skyscrapers, you would only have about 10 feet per floor on average. And in some of the newer ones, you're going to have much higher than that, closer to 12. So over years, we see the amount of ductwork and girders and stuff like that grow. And so we might see a trend that in the later years of being built, we have different sort of errors, which hints at later in chapter 11, something we're not going to cover. You can have 2 explanatory variables in a regression. Not hard. There's another stat class that covers that. That's stat 313. Or if you've taken that and you say, hey, you know, that alone is not enough, I want to sort of head in and pick up a data science minor, then you're going to take stat 324 after, which is a lot of content. 12 weeks. I'm almost in semester state. Okay. 10 weeks of content on just regression. There is one other question that I think, however, that I would like to address if there aren't questions on either the hypothesis test for a slope or the confidence interval for a slope. Okay, so then the last major topic that I think I want you to see is a 100 times 1 minus alpha % confidence interval for, I'm going to call it for beta 0 plus a beta 1 x t. So I could choose a particular x, okay, and I could say, 40 floors. What is the average height of 40 floor buildings? Tell me the average for this particular x. Not hard. We can do it. It's always going to be an estimate plus or minus a margin of error. Here is your estimate. It's going to be beta 0 hat plus beta 1 hat times xp. Okay, so that is your estimate. We're estimating the unknown lowercase Greek letters with the version of them with hats on them. Well, just plug in each of the numbers, beta 0 hat, beta 1 hat, and xp, and then plus or minus a margin of error. And that has to do with always t. Alpha over 2 is the related to the rate of error cut in half, if you will, just the upper tail area. It gives us overall, say, 95% confidence and degrees of freedom, where degrees of freedom is equal to n minus 2, or degrees of freedom error. And I prefer that more general approach, that it works across even other problems. Then we're going to need to multiply that by a standard error, and the standard error is the standard error for our estimator. The estimator being, well, how far off? I'm at the estimator of the actual average height for buildings of 40 floors. That's a number which we can then calculate. Okay, and how far off is your calculation going to be? That's equal to S. And again, S is the square root of mean square error, or sometimes called RMSE, times the root of 1 over n plus 1 over n minus 1 times x p minus x bar over sx squared. You might be wondering a little bit about why this extra weird complication here. I'm going to sort of show you graphically why that's the case, and the lab will walk you through it more slowly. I am spotting, though, here in my inner bits of my equation, it says the further your particular x is away from the average x, the wider your margin of error would be. The more variability you have to have, the less precision you have. Let me show you how to actually get that done with our software. And let's go ahead and clear that. And I'm going to show you this. And I'm going to say, well, we talked about a 40 floor building. We happen to already have one in our data set, but just in case we didn't, let's talk about a 40 floor building. I'm going to just put in 40 floor building. Okay. A fake 60th data point where we have an X value, but we don't have the corresponding Y value. That's a data point that will not be used in any calculations of the slope or the intercept or the standard error or anything like that, but it will allow us to quickly and easily predict the height I would expect to see for a building that's 40 floors. And so you could put in any particular X value you would like to know the average Y of, and as long as you don't put in a corresponding Y, everything works out brilliantly. So under analyze, fit Y by X by friend, I'm going to say the height. It depends on the number of floors. I'm going to click OK, see the graph, and there is no 61st data point plotted because, frankly, we didn't have a Y value. We don't know where in this vertical column entitled X equals 40 that new Y would be. But if I do turn on the trend line, we could calculate what Y I would expect from the intercept, 90.3, and the slope, 11.3, okay? But here's a fun thing. Under linear fit, I could say, I want to save my predicted values, save my Y hats, save my forecasted height. My predicted height for a 40 floor building would be 542 feet. Okay. So you're thinking, well, you just gave me my Y hat. What about the margin of error? Again, that's easy under the linear fit. We could say, I would like to save my, where's this? I have to lean in, sorry. Mean confidence limit formula. Okay, weird way to phrase it. I would have chosen this title myself, but literally a confidence interval for the mean. And please calculate that formula for me and provide me the upper and lower limits. That's how I'm going to interpret that. What is a confidence interval for the average Y for this particular X? Calculate the formula and give me the lower and upper limits. And you can see we are 95% sure that the average height of a building with 40 floors is in the range 527 to 557. Easy to do, yeah? Also under our graph, we can even show that graphically on the plot. So I could do a confidence interval. I'm going to shade it in for our fit, okay? And literally it says, okay, I'm 95% sure that the average height of a building is in this range. And notice for a really tall building, we're less precisely knowing the average than for buildings are close to the average height of, average number of floors. So graphically, we're displaying what are sometimes called the bow tie shape, where the wider out you get, the further from the average X you are, the less precisely we know the average height. And it's really just because if the slope is only slightly off, yeah, the actual average could be much higher, even if quite near the average X, the slope being off, I'm still going to be able to peg the average quite precisely. So our equation from the previous slide, from the previous thing I wrote there on the whiteboard. No, it's not really a whiteboard either. Well, you know, you saw me write down the equation. It's in the book too. The one topic I'm not going to address, but I want you all to know about is there's also, and this will not be on the test, there's also a way of predicting where individual buildings heights will be. Because literally I'm looking here, I'm saying the bulk of these data points are not within the confidence interval, because it's a confidence interval for the average value of height for buildings based on the number of floors. If I want to show you where the individual buildings will be, I do the confid individual, and that tells me here's a range of values that should capture about 95% of actual skyscrapers. And it looks as though in our data set of about 60 data points, we did exactly that, because 1, 2, 3 of the 60 are outside that range. That's pretty darn close to 95%. So let's talk about our 1, 2, 3 confidence intervals that we sort of talked about at the very end. The confidence interval for the slope. Hey, if you want to know the effect of a 1 unit increase in X on Y, that's a confidence interval for the slope. Or if you want to know the confidence interval for like a 100 unit increase in X on Y, like back with our Ninana ice flow data, okay, 100 year, you could put a confidence interval on how much we have the average ice breakup date being earlier now because the 100 years has passed. A confidence interval for the slope will address that question. We just need to scale it up by 100. But if you want to know a confidence interval for a Y value, the height of a building, or the average height of a building, you're going to use the more recent method where you've got that weird root thing with the XP in it. You have to plug in a particular X and you get your forecast out. And from the forecast, you put a margin of error on the forecast, but it's a forecast for what? The average height of a building for this particular number of floors. That's a good place for me to stop for the day. I'm going to stop the share and say, as always, you guys got a couple minutes for questions if you want before I stop the recording. Otherwise, I want to remind you that office hours are going to start in about 11 minutes from now. And then there are other office hours right around 3:30 or so. And then there's office hours, as always, Thursday before this class, and then after the 4 to 5 p.m. class, and then Friday morning as well. So you'll have opportunities to get some questions asked, but please prep in advance with questions you have related to recent material and or the sample final. Any quick questions before I bail out and see you soon? Okay, I'm going to stop the recording then and say enjoy the rest of your afternoon, and we'll talk to you soon in office hours, or later today in office hours, or tomorrow in office hours, or in class.